I'm audible?
Yes, sir, you are audible.
Okay, thanks. You can see my screen, right?
Yes, sir. Yeah, your screen is just.
Okay, thanks. All right, so far we've mainly discussed two problems. One, that of source coding or data compression, where we saw that the minimum rate of compression is given by the entropy, or the minimum rate of compression for a memoryless source is equal to the entropy of the source. And then we looked at the channel coding problem or communication channel, where we saw that the capacity of the channel or the maximum rate of reliable communication is equal to the maximum overall possible input distributions of the mutual information between the input and the output. So the capacity of the channel or the maximum rate of reliable communication is this quantity. I didn't give a proof of a formal proof of this statement, but I just want you to believe this for now. I will not give a full proof of the entire statement, but at least we saw some calculations, some derivations for the binary symmetric channel. So for the binary symmetric channel with crossover probability P, the capacity is equal to 1 minus the binary entropy of P. And one way of interpreting this result is the following. So if the channel were completely noiseless, then you could effectively transmit 1 bit per channel use. So that's the amount of information that you could send in every channel use if the channel were noiseless. Now the channel is adding some uncertainty. So the corruption introduced by the channel is P, and therefore you have to reduce the rate, and the amount of rate that the amount of reduction in the rate that is required in order to ensure that the receiver can reliably estimate what is being transmitted is equal to the binary entropy of P. Right? So in some sense, this is the amount of uncertainty in E. So note that for the binary symmetric channel, the output yn can be given as xn plus en. So the amount of uncertainty in en is n times h of p, and if xn is the transmitted symbol, and we choose xn uniformly at random, then xn contains roughly n bits of information. So the amount of information that yn gets about xn is n minus n times h of p. So one way of interpreting this is that the capacity is equal to the amount of uncertainty in xn minus the residual uncertainty in xn given en. So this is the amount of uncertainty that en is introducing, and that is roughly n times h of p. Right? And another way of looking at the channel coding problem is that of packing balls, and once again using just the properties of the number of sequences of Hamming weight at most np, we saw that the total number of code words that we can fit in such that two noise balls don't intersect. This is all. The total rate that you get is still 1 minus h of p. Right? Where the Hamming distance was defined as the number of locations in which the two sequences differ. Right. So any questions regarding what we discussed in the last class? So I'll wait for maybe 10 seconds. By the way, in case you want to ask any questions, you don't need to put it in the chat box or raise your hand. Just unmute yourself and ask directly.
Sir,
Yes.
while calculating the BSC for this case, when we
Correct.
are taking the probabilities, like the crossover frequency, the crossover probabilities, we say P, right?
Correct.
Should we treat that as conditional probability where probability of Y is something given X is something?
So indeed. So let's see. Let me introduce a new page. All right. So really, what is the capacity equal to, as I've defined, or even before that, what is the mutual information? Ixy is the sum over xy of pxy of xy log p of xy divided by p of x, p of y, right? Now I can write this as p of xy log p y given x, right, divided by p of y. Correct. So there's still sort of a maximization to be done over here. To find the capacity, you need to maximize over all possible input distributions. And really, you should try to do the maximization yourselves. But it turns out that the input distribution that maximizes the mutual information for the BSC turns out to be Bernoulli half. Okay. So so this so if the input is Bernoulli half, so let's do a simple calculation. So suppose that the input is Bernoulli half, then what is the output going to be? What is the output? What is Py going to be? So what is Py
Half and half.
of 0? Yes, I think I heard something, but it was not clear.
Half only.
It's half, right? So probability that y is equal to 0 is the probability that x equal to 0 and y equal to 0 given x equal to 0, plus the probability that x is 1 times the probability that y equal to 0 given x equal to 1. Right? So this is simply 1 minus p times half plus p times half, which is half. And this is also equal to Py of 1. So if the input distribution is uniform, then the output distribution also turns out to be uniform. Now what is Py given x? Okay, so what is, let me put it this way. So our goal is to compute this mutual information, right? So this is xy half Py given x of y given x times log Py given x of y given x divided by Py of y, which is half irrespective of what y is, right? So this, if I split these two terms over here, I get sum over all possible xy of half Py given x log of 1 by half plus sum over all xy of half py given x times log of y given x. Correct? So this is, so what is the first term equal to? So this term over here,
One.
it's 1 bit, right? So it's 1. This is 1 plus, can you say what the second term is going to be? So what is py given x for any fixed x? Or let me put it this way. So take any x, so x equal to 0 or 1. I'll take the half outside. So take the summation over by py given x log of py given x, right? So what is this equal to?
Looks like entropy of y given x.
Correct. So it's entropy of y given x, but at least for the BSc, what is this equal to? So take x equal to 0. So if x is equal to 0, then what is py given 0? So this is essentially 1 plus, so sum x equal to 0 or 1 half of p0 given x log p0 given x plus p1 given x log p1 given x. So what is the term in the bracket equal to? Yes.
Minus 1 by 2.
Sorry?
Minus half.
Minus? Your voice is not very clear.
Minus half.
Minus half? Why?
So P of 0 given any x will be half. Same for 1, and log term will be minus 1.
So what is the probability that y equal to 0 given that x is equal to 0?
Half.
So
Why?
One minus p.
Sorry, can you repeat?
Sir, you were asking y is equals to 0 given x is equals to 0. That's what I was saying. 1 minus p half.
Correct. So the probability that y equal to 0 given that x is equal to 0 is 1 minus p, right? So the probability that y equal to 0 given that x is equal to 0 is 1 minus p. The probability that y equal to 1 given x equal to 0 is p, right? So similarly, p y equal to 1 given x equal to 1 is
Half again.
1 minus 2.
it's 1 minus p, right? Why half?
Okay, okay. I'm taking P as half, sir.
No, so we're talking about a general p, right?
Oh.
And p 0 given 1, this is equal to p, right? So now if you plug these into the term within the brackets, what do you get?
Sir, minus 2H2P.
Correct. So it is minus h2p, right? So the summation over x is outside. So for x equal to 0 or 1, this is equal to minus h2p. So it is 1 plus 1 minus half h2p minus half h2p. So it's equal to 1 minus h2p, right? Any questions?
So what if s to p is equals to 1? Then the information must be 0.
Correct. So when do you think h2p will be equal to 1?
So this Bernoulli half we can get this s to p is equals to 1 or
Correct.
Bernoulli trill.
Correct.
So
And
what does this physically mean, sir? Means there will be no capacity or information containing that, sir.
so if h2p is equal to 1, then can you say something, sorry, when p is equal to a half, right? If p equal to a half, what can you say about the relationship between the input and the output?
Independent.
So if p is equal to a half, then the random variables x and y are actually going to be independent of each other, right? Because py given x is the same irrespective of what x is. So the output is statistically independent of the input. So even physically, it means that we cannot transmit any useful information across this particular channel, right? And that is confirmed by the capacity expression 1 minus h of p, which is equal to 0 bits per channel use.
Okay, sir.
Right? Any other questions? Okay, so at this point, let's have a short quiz. I have sent the link over the chat box. So you can take 2 more minutes to submit your solutions. Is everyone done? Has anyone not submitted their solutions? Is there anyone who has not submitted their solutions? Okay, so I will stop accepting responses. Yeah, I've released this course for everyone, so I think you should get it in your emails. The quiz was fairly simple. The first question was the capacity of the BSC with crossover probability 1. So this is equal to 1 bit per channel use because the binary entropy of P with P equal to 1 is equal to 0. And for the second problem, of course, we just discussed right now, the capacity of the BSC with crossover probability half is equal to 0 bits per channel use. For the third problem, the capacity is at least 1.5 bits per channel use, because you know that the mutual information is at least 1.5 bits. Okay. All right. Okay. So let's revisit the quantity entropy once again. We've seen that the minimum rate of compression of an IID sequence xn is equal to the entropy of the sequence. So the minimum rate of compression is equal to the entropy, which is this formula as you see. Right. Another way of writing the entropy is in the following way. So if you consider the random variable log 1 over p of x. So log 1 over p of x is in fact a random variable because the argument x is the random variable. So it's a function of x, and therefore log 1 over p of x is a random variable. So the expected value of this random variable is also equal to the entropy. Right? So similarly, if we are given two random variables x and y, which are jointly distributed according to some pxy, then the joint entropy is defined in a very similar manner. It is the sum over all xy of pxy log 1 over pxy. And using a similar analogy, this is also equal to the expectation. The expectation is taken over both x and y of log of 1 over p of xy. Okay. And similar to the joint entropy, we also define something called a conditional entropy. And the conditional entropy, so the conditional entropy of x, given that y takes a certain value little y, is equal to this quantity. So it's a summation over all possible x of px given y of log 1 over p of x given y. And the conditional entropy of x given y is so this quantity, the conditional entropy of x, given that y takes value little y, so this is a function of y, right? However, the conditional entropy h of x given y does not depend on the value of on a specific value of y, because it's averaged over all possible y's. So it is the summation over all x of p of xy log 1 over p of x given y. And in terms of expectations, this is the expectation taken over jointly over x and y of the random variable log 1 over p of x given y. Okay, so what is the interpretation of the conditional entropy? We've seen that the entropy of a random variable is a measure of the amount of uncertainty in that particular random variable. So h of x is the amount of uncertainty contained in the random variable x. The larger the entropy, the more the uncertainty, the more random that particular random variable is. And the same holds for joint entropy. So it's just for a pair of random variables. The conditional entropy, on the other hand, is the amount of uncertainty left in x. So given two random variables x and y, suppose that you know the value of y and you want to estimate, or you want to know what is the value of x. You have access to only y. You don't have direct access to x. So the amount of uncertainty left in x is equal to, given that you know the value of y, is equal to h of x given y. So for example, suppose that you roll a particular dice. Okay, you roll a die, and someone tells you that the number is odd or even. Okay, so the random variable y is whether the roll of the die is odd or even. But what you want to know is the amount of uncertainty that is left in X. So this is the amount of uncertainty left in X, where X is the number, whether it is 1, 2, 3, 4, 5, or 6. Now, if someone tells you whether a given number is odd or even, then how much uncertainty do you think is left in X? How many possible values can X take, given that someone tells you whether the roll is odd or even?
3.
3 possible values, right? So, and all 3 values are equally likely, correct? So how much? So what do you think the uncertainty left in X is? So if you have a random variable which takes 3 values, all 3 values are equally likely, then what is the entropy of this random variable?
One.
Why 1?
Sir, can you repeat your question?
So suppose that I have a random variable, let's call it Z. So Z takes 3 different values, let's say 1, 2, or 3. And all 3 values so the probability of taking of Z equal to 1 is 1/3, the probability that Z equal to 2 is 1/3, the probability that Z equal to 3 is also 1/3. So all 3 values are equally likely. What is the entropy of Z?
Log 3 base
Log
2.
of 3.
Correct.
Log
So it's
3 to the
log.
base.
Correct. So it's log 3 to the base 2. Right. So if you have a random variable which takes 3 values and all are equally likely, then the amount of uncertainty in that particular quantity is log 3 bits. Correct? So now coming back to the question, if someone tells you that the roll of a die is odd or even, then how much residual uncertainty is left in the actual value of the random variable?
Uh, 1/3.
So again, we're measuring uncertainty through entropies, right?
Yeah, then log of 3.
Correct. So it's log 3 bits, right? So the amount of, so irrespective of whether y is odd or even, the residual uncertainty about x is log 3 bits, right? And in fact, if you later, so you don't really have to do it now because we don't because it will take some time, but you can compute the conditional entropy h of x given y for this particular event, and you'll see that you will end up with log 3 bits. So if you didn't know whether the number was odd or even, then what is the uncertainty about x? What is h of x?
Log 6 to the base 2.
Correct. So it's log 6 to the base 2, right? So if someone, so originally, if you didn't have any extra information, then the amount of uncertainty is log 6 bits. But if someone tells you, someone gives you side information as to whether the number is odd or even, then the uncertainty is now reduced, and it is now reduced to log 3 bits. So all of this is again intuition. So is there a physical sort of a physical parameter or physical quantity that corresponds to the conditional entropy? Indeed, there is. And that is this, as we saw, that the entropy is the minimum rate of compression for an IID sequence. The conditional entropy turns out to be the minimum rate of compression if you want to do compression with side information. So one classic example is that of compression of a DNA sequence. So typically, if you look at the DNA sequence of two different individuals, then these two are correlated with each other. Right? So suppose that we take a very simplistic model where you want to compress, say, the DNA sequence of one particular individual, but both the encoder and the decoder know the DNA sequence of some other individual. Okay, and so this is what is called a reference sequence. Okay, and this is some side information available to everyone. Okay, and now we want to know what is the minimum rate at which you can compress the sequence xn. If the sequence is IID, which means that across time, so x1, x2, x3 up to xn are all independent and identically distributed. y1, y2 up to yn are independent and identically distributed, but x1, y1 is correlated, x1 and y1 are correlated, x2 and y2 are correlated, xn and yn are correlated, and the joint distribution of xi, yi is pxy. So if this is the setup, then the minimum rate of compression turns out to be equal to h of x given y. So h of x given y is the minimum rate of compression in the case where you want to compress x given a reference sequence y. In fact, so this is sort of what one would expect because the amount of uncertainty in x is h of x, the amount of uncertainty left in x having known y is h of x given y. So the minimum rate of compression would be the amount of uncertainty left in x given that you know y. So this is the case where both the encoder and the decoder know y, but in fact one can show that even if the encoder doesn't know x, doesn't know y, if only the decoder has access to yn, even then the minimum rate of compression is h of x given y. It's a rather surprising result. It's a deep result in information theory, but yeah. So even even without the encoder knowing the value of yn, you can still compress a sequence to rate h of x given y. Okay. Any questions?
So can you explain briefly, like, how can we do that?
That's a little hard to do, but in some sense, so one way of showing that this is achievable is the following way. So basically, what the encoder does is that it takes a random hash of x. So ck is basically, so if you again, I'm talking about fixed length compression. So ck will be chosen as a random hash of x, and the decoder, having known this particular hash and yn, it can somehow uniquely map it to a particular xn with high probability. So even if so typically if you take a random hash, if yn is not known, and you take k to be approximately n times h of x, then from a random hash of length n times h of x, you can reconstruct xn with high probability. Now if you try to reduce k, so if you try to reduce k to something like n times h of x given y, then there will be multiple xn's which correspond to the same hash ck. Okay, so there'll be multiple xn's which correspond to the same ck. But since but now if the decoder knows yn, then it turns out that only a few of these sequences corresponding to the same random hash will be very tightly correlated with yn. Okay, so there'll be multiple sequences which correspond to the same ck, but only one of these sequences is going to be tightly correlated with yn. The others will not be very tightly correlated with yn. Again, I'm being very loose over here. Things need to be more formally defined, and it's not very obvious as to why we can really achieve n times h of x given y. But this is some intuition as to how you can go from h of x to h of x given y only when the decoder knows yn. Does that answer your question to some extent?
Yes, sir. Yeah.
Any other questions? Okay. So we've now seen two different quantities, the entropy and of course a host of entropies. We've seen the individual entropy of x, the joint entropy of x and y, the conditional entropy of x given y. Equivalently, you can think of the conditional entropy of y given x, and we've also seen the mutual information. Now, it turns out that the entropy and the mutual information are related. So we know that the mutual information is this particular quantity. It's summation over all possible x and y of p of xy log p of xy given divided by p of x, p of y. Now let me split this term into two different quantities. So this is sum over all xy, p of xy. I'll skip. I'll omit the subscripts x and y because it becomes easier. So note that p of xy divided by p of x, p of y is the same as p of x given y divided by p of x, because so this quantity p of xy divided by p of y is p of x given y. Okay, so this is log. Now, since this is log p of x given y divided by p of x, I will split this as log p of x given y plus log 1 over p of x. So this is p of xy log p of x given y plus p of xy log 1 over p of x. Right? So what is the first term equal to?
H of x given y.
Correct. So this first term is simply h of x given y. Wait, is it h of x given y?
Yes, sir.
It's
minus
little,
h.
Yeah, exactly. It's
Minus
minus h of x given y. Correct. And what is the second term?
Plus of hx.
HX.
Hx, right? So it is h of x minus h of x given y. So the amount of information that y gives about x is equal to the amount of uncertainty in x minus the amount of uncertainty in x left over after having seen y. Okay, so that sort of conforms to our intuition of what we mean by information. Right? Now again, the mutual information is symmetric, so I can effectively interchange the roles of x and y, and this is also equal to h of y minus h of y given x. Okay. Now let's look at h of xy. Okay, so this is sum over all xy pxy log 1 over pxy. I will write pxy within the log as p of y given x times p of x. Correct. So now if I split this log into two terms, so log p of y given x plus log 1 over p of x, then what do I get? So what is this equal to?
Summation of pxy log 1 upon pxy.
Yes, but that's what I already have over here, right? I
hy
don't
given
want that.
x. Hy
Correct.
given x
So this is h. The first term is h of y given x.
plus
So it is
hx plus
correct.
hx.
So this is h of y given x, and p and summation over all x y of pxy log 1 over p of x is h of x. So intuitively, the amount of uncertainty in x and y is equal to the amount of uncertainty in x plus the amount of uncertainty in y, given that you already know x. Correct? So this is what is called a chain rule of entropy. Right? So in some sense, if you think back to the problem of compression, now instead of compressing one sequence, if you want to compress two different sequences, xn and yn, where x and yn are, so xi and yi are correlated, whereas across time x1, x2, x3 up to xn are all independent. Now in this case, you can either design a compressor to jointly compress x and y, so a single compressor, right? And the total rate that you can achieve is equal to h of xy. Or what you can do is that you can construct two different compressors. So first compressor compresses only xn, right? So you get C1 K1. The decoder takes only C1 K1 and outputs xn hat. or you can so the first is jointly compressing x and y. The second is you first compress x and then use x as side information to compress y. So this decoder will take as input xn hat and output yn hat, right? So you can do sequential compression. You first compress x and then use x to compress y. So in this case, k1 by n, so the limit is k1 by n, let me denote this by r1, k2 by n is r2. Then as n tends to infinity, you can achieve r1 being h of x and r2 being h of y given x. So the total rate is r1 plus r2, which is h of x plus h of y given x, which is still the same. So it's still h of xy. All right. So this is one way of thinking about the chain rule of entropy. So let's see what we've seen so far. We've seen that the mutual information Ixy is equal to h of x minus h of x given y, h of y minus h of y given x, and that h of xy is equal to h of x plus h of y given x, but you can also show that this is equal to h of y plus h of x given y. Okay. So now can you say what is h of y given x in terms of h of xy and h of y? This is just h of xy minus h of y, right? And if I substitute back here in the expression for the mutual information, what do I get? Sorry, I guess this should be
H of x.
1 second. So this should be h of x. Correct. Thanks for pointing that out. So now if I plug this back into the expression for mutual information, what do I get?
hx plus xy, hy
So it's hx
plus
plus hy
minus hy given x.
minus, are you sure?
Minus hy given x.
Are you sure it's h of y given x?
Minus x comma y.
Yeah, so it's h of xy. Right, so the mutual information is h of x plus h of y minus h of xy. So all of these are three equivalent ways of evaluating the mutual information. Okay, so any questions? If not, we'll end the class for today. If you have any questions, then I can answer them here.